When viewing microwave observations in real time, ambiguities can arise in how to interpret them. For example, one value of brightness temperature could correspond to two very different atmospheric states. In this module, we'll address these ambiguities and discuss how to use multiple bands cooperatively to interpret microwave data. We'll look at a couple of oversimplified atmospheric states to demonstrate the point, then we'll look at some real data. Let's first suppose that we have an idealized, homogeneous atmosphere that has the same temperature throughout its entire depth. We'll make that temperature 260 K and make the surface temperature 300 Kelvin. We will also assume that we are over the ocean and that the emissivity of the ocean varies by frequency, as shown at the bottom, with emissivity increasing as the frequency increases over the range of SSMIS channels. The equation for estimating brightness temperature for a homogeneous atmosphere is shown at center, and we'll fill in the lines in the chart at the top of the table using that. We'll consider a completely dry, cloud-free environment with optical depth of 1, with direct transmittance of 1, a moist environment with some shallow clouds, the moderately dry cloud-free environment in between those, and then a moist environment with deep convection. These environments will have different optical depths, and those optical depths will also vary by frequency. Suppose those optical depths are like those shown in this table for the 4 different environments and 4 different frequencies. We'll show an example of the moderately dry environment at 22 GHz first. We can plug in values for emissivity at 22 GHz and the appropriate temperatures 300 and 600 and the optical depth 0.5 into this equation to get a brightness temperature, and if the math is done correctly, we'll get about 232 Kelvin for this example. We can follow the same exercise for all of the combinations of optical depth and emissivity given the same atmospheric and surface temperatures and come up with the values shown at the top. Generally, brightness temperatures are warmer at 92 GHz than at other channels because the 92 GHz channel is very sensitive to water vapor, and when cloud drops are present is highly susceptible to scattering as well. This means that emissions from the poorly emitting ocean do not reach space. Likewise, as the optical depth increases for each channel, going from left to right in the table, the brightness temperature increases. Note, though, this is for an unrealistic single-layer atmosphere. A more realistic atmosphere is more complicated. Our equation that assumes a homogeneous atmosphere does not work anymore. Instead, we must integrate the last 2 terms over the optical depth of the atmosphere as a function of height. I've selected a few possible values of the quote-unquote representative temperature of the atmosphere by assuming where the peak of the weighting functions for each band might be located in the various environments. We'll plug these air temperatures into our linear equation to create a first guess of what the brightness temperature might be in a more realistic setting. Note that in the completely dry environment, I've left the table blank because the direct transmittance is 1, and so the atmospheric temperature is unimportant. When we do this, we get the brightness temperatures shown at the top by plugging in the values into our equation again. The channels for which the atmospheric is more transparent, like 19 and 37 GHz, generally see an increase in brightness temperature relative to the homogeneous atmosphere that we saw before, while the 22 and the 92 GHz bands experience a decrease in the brightness temperature in the optically deep environments, such as when deep convection is present. We can sketch how brightness temperature evolves as a function of water vapor concentration or optical depth, which is done here with brightness temperatures on the y-axis and some non-dimensional quantity of water vapor concentration on the x-axis. For the homogeneous atmosphere, shown at top, the brightness temperature eventually asymptotes to the atmospheric temperature for all frequencies if enough vapor or liquid water is present to absorb or scatter all surface emissions. However, for the more realistic atmosphere at bottom, brightness temperatures first rise as vapor increases, but then fall again. This happens more quickly as a function of water vapor concentrations at frequencies that are more susceptible to water vapor absorption or scattering by hydrometeors, such as 92 GHz. But if we kept extending this blue line for the 19 GHz even further along the x-axis, it too would eventually fall down. What this means to an observer is that one brightness temperature could represent two very different atmospheric states. In this case, a 190 Kelvin brightness temperature at 92 gigahertz could represent a totally dry atmosphere at this red dot, or deep convection. This is reminiscent of the figure shown previously in this lecture series, showing how rainfall estimates over ocean changed as a function of frequency and brightness temperature. Lower frequencies experience some ambiguity as well, such as this 18 gigahertz line for ocean, meaning that I didn't select the most realistic values of the average atmospheric temperature for emissions in our more realistic example. For example, a 240 Kelvin brightness temperature at 18 gigahertz could represent a light or a heavy raining state. However, if we consulted the 91 or 85 gigahertz brightness temperature at the same time and location, it would be much higher for the lightly raining event than for the heavy rain. So for example, at 10 millimeters per hour, our 85 gigahertz would be up here around 240 as well. Actually, it would be around 220, and at the 50 millimeters per hour at 85 gigahertz, we'd be at a much lower brightness temperature. This comparison helps us quickly overcome the ambiguity and interpret the data in real time. An example of such ambiguity over land is shown here in GMI brightness temperatures at 10, 19, and 37 gigahertz. Radar reflectivity for an afternoon in Texas is shown at top left. It shows a few cells containing some locally intense rainfall. In the GMI data, the cells are apparent within the white circles. Actually, another cell over here. However, especially at low frequencies, looking at this bottom right image, we can see more surface emissions even in heavy rainfall. Therefore, the difference between these lakes that are labeled over here in the bottom left panel and are also seen as these splotches in the bottom right panel, which are poor emitters, and then the storm cell itself, these differences are small. By looking at just the 10 gigahertz brightness temperature, identifying lakes from storms can be challenging. Note that the emissivity of the land is generally much higher, close to 0.9, so the brightness temperature over clear air land is higher. Incorporating the 37 gigahertz data, however, yields some better insight into which of the so-called cool areas in the 10 gigahertz image are actually convection. A similar example from SSMIS is shown over the ocean in the Arabian Sea. Shown currently is the 91 gigahertz brightness temperature. The deep convection is obvious and is denoted by the red colors throughout the image. However, more optically thin convection that surrounds the red is denoted by green and yellow. In the far left of the image, over here, green and yellow colors at the mouth of the Persian Gulf look the same as the optically thin cloud. Just looking at this image, it's difficult to tell which is cloud and which is not, outside of the deep convection in the red. 37 gigahertz brightness temperature also identifies the cloudy regions as areas of relatively warm brightness temperature, or actually relatively cool if you're over land. But the mouth of the Persian Gulf now has a very low brightness temperature, like 160, 170 Kelvin. This tells us that the mouth of the Persian Gulf is actually cloud-free. It is probably a particularly dry area over which even the 91 gigahertz channel was able to detect some surface emissions. Another product available operationally is the PCT product, which stands for Polarized Corrected Temperature. The general formula for PCT is shown at bottom and is a weight of the horizontally and vertically polarized brightness temperatures in the same frequency. The capital theta is a coefficient that must be determined prior to the product being generated. As a forecaster, you wouldn't be concerned much about what the coefficient is. The PCT product will generally highlight just the deep convection and surrounding clouds. Note that the color scheme is going to vary depending on the source of your data and the frequency you're looking at. Finally, we can return to our example over Texas and compare vertically polarized brightness temperatures in several bands over here on the left, now including 89 gigahertz in the top row, to the PCT product for each channel on the right. The lakes are especially apparent that were especially apparent in the low frequency imagery over here are now gone, and the convection remains highlighted. Still, because the atmosphere is so transparent in the low frequency microwave, consultation of multispectral data instead of just a single channel is prudent to accurately interpret the scene.